Today I will show how to prove sum of squares formula. This formula is very useful because it allows us to compute sum of squares of n consecutive natural numbers in very simple way. Notice this formula can be written using sigma notation or it can be written using expanded notation. This statement holds true for any natural number n. That means that we can use mathematical induction, and that's actually how we are going to prove this statement. So we will use mathematical induction. First step is a basis, and I want to show that this statement holds true when n is equal to 1. When n is equal to 1, on the left side I have only one term, 1 squared. And in this case, sum of squares of all natural numbers up to 1 is equal to 1. Then I want to check that formula holds true. That means I want to find value of the expression on the right side when n is equal to 1. So we just plug in n is equal to 1 into formula. You have 1 times 2 times 3 over 6. And we can see we have 6 over 6, which is equal to 1. That means that formula holds true when n is equal to 1. And the next step is the inductive step. We assume that formula holds true when n is equal to k. So we assume that 1 squared plus 2 squared plus and so on plus k squared is equal to k times k plus 1 times 2k plus 1 over 6. And this is a statement when n is equal to k. And now I want to show that statement holds true when n is equal to k plus 1 for next natural number. We want to show that statement holds true when n is equal to k plus 1. In other words, that 1 squared plus 2 squared plus and so on plus k squared plus k plus 1 squared is equal to, and we want to find value of this expression when n is equal to k plus 1. So this is equal to k plus 1. The second factor is equal to k plus 2, and the last factor is to k plus 3. Divided by 6. So you want to show that this formula holds true. And let's consider left-hand side of this expression. So let's consider some 1 squared plus 2 squared plus and so on plus k squared plus k plus 1 squared. We assume that formula holds true when n is equal to k. So we can apply this formula for first k terms. That means that sum of first k terms is equal to k times k plus 1 times 2k plus 1 over 6. And you want to add the last term, and the last term is k plus 1 squared. And now I want to show that this expression is equal to expression on the right-hand side. So I want to simplify this expression. And first step, it is natural to factor out k plus 1. So let's factor out k plus 1. And we have k times 2k plus 1 over 6 plus k plus 1. Now we can add these two expressions. Common denominator is equal to 6. So this is equal to k plus 1 times k times 2k plus 1 plus 6 times k plus 1 over 6. So you can add this to expression. Common denominator is equal to 6, so we need to multiply k plus 1 by 6. Now let's distribute k and 6 and combine like terms. And we have k plus 1 times 2k squared plus k. Then we distribute 6 and we have 6k plus 6 over 6. So we can distribute k, we can distribute 6, and now let's combine like terms. We can combine k and 6k. So this is equal to k plus 1 times 2k squared plus 7k plus 6 over 6. And now it's very difficult to see that these two expressions are equal, because this trinomial is equal to product of k plus 2 times 2k plus 3. So we can write this as k plus 1 times k plus 2 times 2k plus 3 over 6. And we can check that indeed product of these two linear factors is equal to this trinomial. So let's multiply k plus 2 by 2k plus 3. So we want to multiply k plus 2 by 2k plus 3. We can use distributive property. We have 2k squared. Then you have 3k and 4k, so we have plus 7k and plus 6. So indeed we can see that product of these two linear factors is equal to 2k squared plus 7k plus 6. That means that statement holds true when n is equal to k plus 1, and that means that this formula is proved. Because we proved formula when n is equal to 1, we assume the statement holds true when n is equal to k, and we proved that formula holds true for next natural number n is equal to k plus 1. And that means that this formula is